Okay. All right, so let's get started by making a short recap of what we did during the last lectures. So we went through all the theory and the formalism and the mathematics that is useful to investigate dark energy, to characterize it, and with that to see what is the evolution of the universe in terms of its components, matter, radiation, and the dark energy field itself. Then we started, after having completed that part, we're starting now to add some complication, right? So we start to introduce coupling in the quintessence field. So now we are going to have a coupling term between the dark energy field and matter component. This means that there is an energy momentum transfer between the two. They are talking one with each other. They're just not sort of independent. I mean, first they were kind of coupled, if you wish, through gravity, in the sense that dark energy was influencing the expansion of the universe, and matter was feeling this expansion of the universe. But there was not a direct interaction between the two, okay? Sort of this indirect interaction. Now we have a direct interaction, and we introduce that by basically introducing, what you usually do, an interaction term in the Lagrangian. Okay, so you could start in this way, you define interaction term in the Lagrangian, you use the relationship between the energy momentum tensor and of the given fluid, of the given component, and its own Lagrangian to then derive conservation laws and so on and so forth. Okay, so what we did now, and of course, when you want to impose conservation law, that's what you have to get in our case, right? Now we have radiation, matter, and the field, so we have the three components, and the total energy momentum conservation law reads like that, okay? So what's going to happen now? We are going to have an energy momentum exchange between these two guys, and therefore, if this guy is sort of losing energy momentum, this guy is gaining it in the very same way, opposite, equal in opposite direction. Therefore, a convenient way to find out or to impose some coupling between the two terms is not by starting with a Lagrangian and getting the energy momentum tensor as a consequence, but just by modifying directly the conservation laws, okay? By, for example, for matter and the dark energy field, introducing this energy momentum current, okay? Energy momentum current, which has an amplitude which is the same for the two guys, but with an opposite sign, okay? That symbolizes, or let's say, is expressing, not symbolizing, is expressing exactly the energy momentum exchange between the two, okay? Here you can play in several ways. You can impose linear coupling, you can try out linear coupling, non-linear couplings, or whatever. What we did was to use this coupling, which is linear. You see there is this Q term which expresses the strength of the coupling going to zero, so no coupling to, very, very strong flux between these two terms, and proportional to the trace of the energy momentum tensor and this gradient, this covariant derivative, sorry, of our dark energy field, okay? This sort of coupling is inspired by brane-Dicke theories that we are going to see also in next lectures, okay? So we are going to see why this term is coming about. In any case, now we just start by assuming this coupling, okay? If we are assuming this coupling, then we realized that if that's the case for all species in our universe, including radiation, then this guy is actually decoupled. And that's for the very simple reason that the trace of the energy momentum tensor of radiation is zero. Okay, that's traceless. and therefore it gives zero coupling. Okay? Not because Q is equal to 0, but because Tm is equal to 0. Okay? That's what we got. Now that we have this conservation law, if you want, or non-conservation law, depends how you want to look at that, we can look for the dynamic of our field. You can look at the equation of motion of the fields, and for example, by investigating the continuity equation. So what you do, you get your conservation law, so this guy here for matter, field, and radiation. You see, we have the field, matter, and radiation, and we get the 0th component. You see, nu equal to 0. So that's basically energy conservation, energy density conservation, which is the continuity equation. So whenever you do that, you can see that you don't have anymore the familiar expression that we had in the previous lectures in which we had this term, which is unchanged, and equal to 0. Okay? If something, if the energy density in a certain location, in this case for our field, is changing, that's because there is a sort of a gradient that's related to a gradient to the field itself. Okay, so there is an exchange with another location, if you wish. Okay, with matter is easier to visualize that because matter is conserved. If you get a lower energy density here, because it's transferred somewhere else. Okay, that's for example, we can transform into a number density law, for example. But you see now that the coupling pops up here for the very simple reason that we find it here. Okay, that's it. So basically, this term is this guy here, and this term is this guy here. You basically see we have a dot here because nu now is 0. That's the time derivative. Okay, and that's the case for the field. For matter, the only difference is matter, as we intended, is dust, therefore is pressureless, so that's equal to 0. And then we got radiation. And of course, you see there is an H popping up here in the continuity equation. Therefore, to close the system, we need the Friedman equation that is going to tell us how H is relating to the densities. Okay? Now what we can do, and actually what we already did, was to get the continuity equation of the field and express the density and the pressure of the dark energy field with respect to the kinetic and the potential term. Right? That's we did already, so it's just a mere substitution of these two expressions here and here, just that. And you get in here, sorry, as well. And you get this expression. See that we have this phi dot here that conveniently cancel out, so you see all drops out, and we are left with the usual Klein-Gordon equation that we studied in detail, where the only difference now is the coupling term, which is here. So now we don't have anymore a 0, but we have something which is different than 0. Okay, so this is, you see how it is, how the equation of motion of the field, the energy field, is affected by matter. So you can see this coupling as a source term in action. What we are going to do now, I'm not going at the blackboard, because I'm going to repeat again the same scheme that we did for dark energy in general, and when we introduced radiation as well. And when we introduced radiation as well, we learned that the phase space becomes three-dimensional, and the board is difficult to manage. Plus, we are going to have quite a sizable, big table expressing and showing us all the critical curves that we have in the phase space. Therefore, I will remain at the blackboard for this discussion. Also because you are now you're kind of used to this way of dealing with the metal. So, okay, so that's what happens. We have this new term in the Klein-Gordon equation. As usual, we define our dimensionless parameters, x1, x2, and x3, that we already met when we introduce the radiation. Okay, these are the usual ones that we had from the start, so the kinetic, related to the kinetic and the potential of dark energy, and radiation, okay, just by construction, so these terms are derived by construction, such that the Friedman equation leads to this expression, okay, which is obtained, again, because we are assuming flat geometry. Okay, flat geometry, that's what we have. Since this expression with using this expression. So you see, we realize that this guy here, this x1 square plus x2 square, is actually the omega phi. And again, by definition, that's just simple substitution, this is our omega radiation. Okay? That's what we already seen. And of course, that's just the rephrasing of this expression. Again, using, since phi dot and v are expressed in terms of x1 and x2, and the density and pressure of dark energy are given by phi dot and v, we can express rho and p in terms of x1 and x2. And if we get the ratio of these two quantities, we get the equation of state, which is this one. So again, you see that phi, the equation of state of our field, is related to x1 and x2 only. And the effective equation of state, now by including also radiation, we have done the derivation for the case that we are discussing, gives this additional contribution given by radiation itself. Okay, so we had the usual 2 plus the radiation term. Now here it starts to be the difference with respect to the construction that we have seen already when we dealt with two matter fields, radiation and the matter, the real matter, let's say, like dust. And we go for the usual tricks. So we want to study the phase space, and we want to transform our Klein-Gordon equation from one second-order differential equation to a collection, now 3, because we have 3 components, phi dot, v, and radiation, expressed as derivatives, or as first derivatives of x1, x2, and x3. Okay, so from one second-order differential equation, we go to first-order differential equation. Okay? Now, you understand that we get exactly the very same results that we had before, when we had dark energy and dark matter not coupled. We get this additional term, where you see the Q popping up linearly with respect to all other terms. Why is that, and why is not appearing in the other terms? Well, that's because here we're talking about x1. And what is x1 related to? Phi dot, right? And when we were making the derivation here, if you go back to the computations that we already did, basically this is coming from the Klein-Gordon equation for the field. So we basically, what we did was to isolate phi dot, such we can express in terms of x1. x1 is equal to all of that, and this gives us this Q rho contribution that before we hadn't. Okay, so exactly the very same steps that we had before. The only difference is here through x1 because it contains the coupling. And you see that it's linear. And this is linear, so that makes completely sense. And look what we have here, and look what we have here. Is Q rho m. What is rho m? The energy density of matter. What is the energy density of matter? Well, where are we? Here is this one. You see, that's rho m divided the critical density. Therefore, you understand that just by reshuffling a little bit the equations, we get the Q here, which is coming from here. Rho m gives you omega m. Can be transformed into an omega m. Okay? And omega m is this guy here. Okay? So again, that's the imprint of Q, the coupling term, and that's the imprint of rho m, and this appears linearly. Okay? Through the definition of x1. That's it. Okay? So that's the key difference that we get. Then what we do, once we have our new set of differential equations to be studied, again, we realize, of course, that we don't have numerical analytical solutions, but analytically we can identify the critical solutions, the critical points, just by looking at the solution for which these derivatives are equal to 0. Okay? So again, usual game that we already played. We identified all the solutions that are satisfying these conditions, and boop, 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 we go from A to G. Okay, so we have quite a pile of them. And there are key differences with respect to the case of radiation without coupling between dark energy and dark matter that appearing just here. So if we take the first three, A, B, and B1, look the value of X2 and X3. Now I am if we have our phase space, again, well, that's not very straight, anyway, X1 and X2, that's the physical part where the omega m is positive. We have the point A, which is at 0, 0, for radiation, and for X3, which would be in this third dimension, that now is not relevant. You see that for A, the points A, B1 and B2, X3 is equal to 0. So they are on the board. Okay? Then we got for B1 and B2 exactly the same location that we had for all the other cases. One is here with the -1, and one is here. So we have B with the positive, so that's B2, and that's B1 for -1 at 0 with respect to X2. Okay? And they're fixed there. Now look the difference. Point A. Without coupling, Q is equal to 0, and it's fixed here, as before. But if Q now is different than 0, we are going to be away. For example, we might be living here. Or if the coupling is even stronger, we are here, or here, or here, and so on and so forth. Okay? That's because we have this Q here. So if Q is equal to 0, no coupling, our guy is like here, in perfect agreement with what we had before. If Q is larger than 0, you see, well, it depends on the sign of the coupling and on how it's defined, but you see that there is a deviation. That's the physical point, therefore, is going to go in this direction. Okay? Different than 0. Fixed. It's not changing as the universe is evolving or anything of that. There is no lambda there, which might be changing as a function of time. Now we are assuming, I mentioned the other time, I should have mentioned it again, we're assuming the Q, in this case, is a constant which is universal. So it doesn't depend, which universal means that it doesn't depend on time and on space. Okay? So we are going to get A in some other location. Then we have other points which are familiar, and these are C and D, which are similar to the one that we had before, except for the fact that we have some minor modifications here. You see that the Q is popping up here, as well as here, 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 and here. Okay? So there are modifications that are occurring. And again, as we have seen in the very same analogy of what we have seen before, these two guys could be responsible for acceleration. Okay? The difference between the two is that this critical point represents a field-dominated epoch, okay, like the one that are going to experience the universe in the future, and this other one, instead, since Q is going to be typically small, this contribution is going to be subdominant with respect to matter. Therefore, we have a matter domination in this case. Okay? Still with some acceleration, that's because the matter field that we have there is sort of a little bit weird in terms of the equation of state parameter. Okay? Nice. And then we have these other three guys here that are, again, modified with respect to what we have seen when we had no coupling. So we have three additional points because of radiation. That's because we get a third dimension in our phase space. And again, we had this Q, which is popping up in various locations, here, here, and here. Okay? So you see how this is changing. And all of these three epochs, look at the effective equation of states, are corresponding to a radiation domination epoch. Okay? Radiation domination epoch that you can also see here as well. You see, also Q is basically the effective equation of state of our universe is the one of radiation. Okay? Nice. Let's give a look, because we have a lot of critical points, but what we actually need are 3 phases to describe the stages of the evolution of our universe. We had an initial radiation domination epoch, matter domination epoch, and acceleration dominated by the field that we are experiencing nowadays, okay? Therefore, what we need? We need 2 initial points out of which we can escape, because if they would be stable, we would be sitting there. No? If the initial condition lead us there, then we are trapped. Therefore, we need these points to be saddle points. Whereas the yeah.
Why cannot be radiation or be unstable?
Because it will last too little. Because then you would be in this unstable, like the point B1 and B2, which are kinetically dominated by the field, by the dark energy field. They are unstable point, and if you are there by initial condition, you go away immediately. Okay. Whereas in saddle point, you're kind of attracted there. You do like whoa, so you stand there a little bit, and then you go away from it. Okay, exponentially. So exponentially and exponential, but you stay there for a while. Good. And that's the case for lambda constant, okay? Because then we have seen that one lambda is not constant. You can have a critical point, which is a stable point. You are there, you're trapped. Lambda is changing, is going to 0, as we have seen, and it becomes a saddle point. We are free to go away, okay? So this is the case for lambda equal to constant. So an exponential, just to remind you, this is an exponential potential for dark energy, okay? That's this model. Nice. Okay, so let's see. We have all of this pile of critical points, but we need those that are representing our actual universe. And therefore, what we do? Well, we have to look for let's start from identifying a radiation, a matter domination, and an accelerated phase. Okay, so, yeah?
Regarding the question before, why do we want to stay in radiation era or something?
Well, because a radiation epoch must last enough to explain, for example, the Big Bang nucleosynthesis. Okay, so we need to stay there for a while, and it's more likely if we are next to a saddle point than an unstable point. And that's because of the initial conditions. Because if you have, you have 2 points which are unstable, let's say B1 and B2, for example, which are here, whatever our initial conditions, we are going away from them. We are not going toward them. So to be in those regions, the initial condition must be set such that we start from them, from an unstable point. So they are completely not relevant for a discussion, okay? Whereas saddle points, yes, that's interesting because we can fall. Even if we start with some whatever initial condition, there is the possibility that we're attracted there. Okay, so it's more likely to have them. So that's why.
It can also be not a saddle point, just a random point that happens to be in the path towards the stable point.
Yeah, that might be, but this would be just one of the stages of the evolutions. Because, for example, when we sketched the critical points, we had like, what was it? I don't remember. Our the point, how did I call it? So it was C, it was up here, okay? And then what you will get, if you say a random location, then we will be attracted here, then we go up here, and you say a random position, we are in this stage of the evolution of the universe. Okay, so we are in the transition phase between one domination, if you want, and another one. Okay? No, if you say a random point, so these are special points. Okay, so these are special solutions in which x1, x2, and x3 are constant. Okay, these are just a special point. If you take a random location, then you're going to move in the phase space along one of those trajectories. Therefore, if you start from this initial condition, this is an unstable point, we must run away from it. This is a stable point, we must fall into it. Okay? Therefore, we know that if we take some random location, x1, x2, and x3 are not constant, and they're pointing in some direction. And by the construction instead of the critical points, we know that must be going in this direction. Okay? And they must exist. I mean, we are populating, we are living on a track along this phase space. Okay? And these points must be populated because we have a transition between two phases. There are going to be phases, for example, in which we have equality, epoch, between matter and radiation. The two omega m's were the same. Okay? This one will be one of the points transitioning between two critical points. Okay? Okay, good. Moving on. Let's start now to see the good parts, the good critical points. So let's start with radiation. So we know that we have to pick up between these three guys here, these three critical points. But now we need to have some constraint on Q and lambda, such that, for example, the Big Bang nucleosynthesis, for the formation of helium, deuterium, and all of that, is respecting what we observe. Okay, so we must last long enough. The radiation epoch cannot be too short, and there are constraints on that are then resulting on Q, on the values of Q and lambda. Okay, therefore we would need these two constraints to be fulfilled, but these are excluded. Okay, so Big Bang nucleosynthesis tells us that the point F and G are not good points. Okay, so this is excluded. These are 2 points are excluded not because of theoretical reasons, but because the observations tell us that we are never been there. Otherwise, we would have the wrong radiation epoch, which should be this one. Okay, so observational reason. So our epoch is E. That's the nice one. Then we can move on. So our universe evolves, and we enter in a matter era. And the 2 critical points responsible for the metal era are the point E and D. So this one and this one. Okay, and you see that it's a matter domination epoch. Now I'm giving you a subtle point about the point A, but anyway, they are matter dominated, and you see it from omega radiation. Well, that's 0, so that's completely irrelevant when we are there, and whereas this guy is very small, and therefore omega m is the dominant species. With a difference now with respect to the matter domination that we are used to think of, because now this guy here is not 0. And if Q is large enough, we have a non-negligible contribution of omega phi. Okay? Dark energy would not be negligible. That's why this epoch is not called matter domination, but is called phi dm domination epoch. Okay, so it's dominated by dark matter, by matter in general, and there is a contribution from the scalar field, from the dark energy. Okay, so phi dm epoch. Okay, we will see later also the values that we expect as a difference once this model is in place. And a nice thing of these 2 solutions is that they are both scaling solutions. Because if we look for Q, that must be small, because otherwise we would break the local constraints that we have on gravity, okay, on the motion of matter in our local universe, in our solar system, for example. Then we know that Q must be very small, such that we have this sort of matter domination. So you see, if for A, where am I lost now? If for point A, Q is very small, you see that this is negligible, and therefore it's matter domination. That is what we need. If we are looking for the point D, then lambda must be very large, much larger with respect to Q. So D, you see, we must have, again, you see there is this contribution of lambda, we must have this ratio, this balance to be fulfilled. Okay? In this case, in both cases, you see we have a constraint again on Q and lambda, which are fine, so they will be observationally acceptable. And with that, we get the equation of state, which is given by meta, and we have the meta revolution that we expect. Great. But now we need to consider the stability, right? And therefore, we can look at the eigenvalues of the point A. So we have mu1, mu2, and mu3. Again, three eigenvalues because our phase space is three-dimensional, where we have these two guys that are always negative. Okay, that's because Q must be very small. So minus 3/3 and minus 1/2 are dominating, and that's negative. Whereas the sign here can be different than 0. That's because of lambda. Okay? Therefore, we can have a scenario in which this is a saddle point, which is what we would need. Okay, remember lambda is constant. Therefore, if this is a saddle point, it remains a saddle point. If it is a stable point, it remains a stable point. And we want this constraint to be fulfilled, so this value to be larger than 0, therefore lambda larger than a certain value, otherwise this guy would be negative and would be a stable position. Okay? Therefore, to have a saddle point, this condition must be fulfilled. That's nice. That's nice. So this is a good point. We cannot exclude it. Then we have the other candidates, which is the critical point D, which has these three eigenvalues. So we have mu1, and then we have mu2 and mu3. Okay, so you see this looks like one equation, but there is a plus and minus. So these are two eigenvalues. So we have 1, 2, and 3 eigenvalues. Okay, and they are all. And in this case, they are all, this guy is positive, therefore all of them are negative, 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 because remember the Q is very small, and which is going to tell us that is a stable mode, because when this guy under the square root is positive, or we have a stable spiral, but still stable points they are, because this guy is complex. Remember that we have a stability points that can be like a standard stable one, where we fall into the critical points, or when we have the square root of the content of the square root, which is negative, then we have a complex term that gives us a spiraling pattern toward the stability. But doesn't matter, that's just a detail, is a stable point. We go there, we stay there. Lambda is constant, the nature of the critical point is not going to change, we are stuck. Therefore, no. Okay, so this is not from an observational constraint, but theory tells us that we using lambda constant for that specific model for dark energy, this is excluded, ruled out from a theoretical point of view. Therefore, A is our guy. Okay, we have our matter domination, epoch, which is a saddle point. Then we want our acceleration that can be given, that is given by C and D, as we have seen. So we have point C and point D, where you can see the condition for the acceleration that is given here. Okay, and you see that we have two opposing conditions, because here we have lambda and here we have also a Q. And now we need to understand if the best candidate is the point C or the point D. Both accelerations, but let's see, according to their stability, which one is the preferred one. So again, we go with C, we look at eigenvalue 1, eigenvalue 2, and eigenvalue 3. And what we would like to have, well, we would like to have a stable point, because we want our universe to end up there, because that's the most likely trajectory that is left to be covered. And therefore, this must be negative, this must be negative, this must be negative. And to have a stable point, that's the condition that we have. On the other hand, for the point D, the condition for acceleration is going to be this one or this one, because otherwise we would not achieve this minus 1/3 limit for the effective for the effective equation of state parameter to give us an acceleration. Therefore, from that constraints, these must be the limits that we have on these two guys. And the stability point tells us that lambda should be this one. So you see, this guy are actually this lambda times q plus lambda, lambda times q plus lambda, you see that's the same term, are going to give us the discrimination between having C to be a critical point or D to be a critical point. You see that the sign of the inequality is opposite, okay? So according to lambda, we are going to fall or on C or on D, okay? So lambda decides which one is going to be the case, okay? Let's leave it now for a moment, and let's make the summary. So we have radiation, we have seen is the point D, which is a pure radiation domination epoch. You see 0 and omega r is equal to 1, with an effective equation of state of 1/3. Standard radiation domination. Then we have matter, which is the critical point A, which has been chosen between the three, because the three available one, because the other two were excluded by observations for the BBN, which is this phi dark matter, phi matter dominated epoch. You see that matter is larger with respect to the contribution of omega phi, but omega phi is not negligible, okay? If this would be negligible, completely negligible, then we are just not considering a coupling term, in effect, okay? So it would be the case that we had before. But now we have this contribution of omega phi, which is there. And the condition to fall in this location is this one. That's the constraint that we have, okay? Where Q is small for observational reason, because we must respect the dynamics that we see within the solar system. Then we have, we need to look for acceleration, and we have two scenarios. So we have these two critical points, and the stability condition is given by these two terms. Therefore, we have to how you say, they're both variable. But if we now look at the constraints to have acceleration that we have seen before, here we have acceleration when lambda square is smaller than 2. It was coming from W effective smaller than -1/3, the standard constraint for the acceleration for our universe. Whereas here we have these two constraints, which are kind of competing one with each other. Okay? Therefore, to obtain these two constraints is more difficult. Okay? They're kind of, if you want one, you're kind of opposing the other one. And therefore, the point C is the more likely one. Okay? You don't need specific fine-tuning, and you don't have conflict between these two say criteria, and for example, the one of matter domination. Okay? So with C, it's very easy to get your lambda. You see omega phi, something that is lambda-like, so you see omega phi, which is -1 plus a difference, and everything works perfectly. So that's our universe, which in the end looks like this. So you see we go from E, radiation domination, we are here. We go down, we're moving toward matter domination, which is here, where the density starts to grow. But you see that once we are in this sort of matter domination, the contribution of dark energy is non-negligible. It's 5% in this case. So it's not much smaller than 0. It's not a 1 per million or 1 per mil. Okay? It's 5% or so. So you see that we have this mixed phase. And then we enter in we go toward the critical point C, which is a stable point, and the contribution of dark energy grows and becomes dominant and give us an accelerated phase when we hit the desired barrier, with an evolution that you see for the equation of state parameter that goes toward -1, but is slightly larger. Okay? So key difference when we have this coupling is that omega phi, that's a standard dark energy as well, is a little bit smaller. The equation of state of our dark energy is slightly smaller than -1, and we have a phi matter dominated epoch, which is here. Okay, so we have a contribution of omega phi, which is non-negligible, roughly 5%, 5-6%. Okay, that's nice. Good. Now, how this effect is observable? How can we possibly measure Q? Well, we can immediately see that we have this phi dm domination here, which affects the expansion of the universe. So the expansion of the universe is not the one that we have in a case of non-coupling. And therefore, if the expansion of the universe is now affected, the distance of the last scattering surface, the CMB, from our set is going to be modified. The distance changes. What does it mean? It means that if we look at the power spectrum of the cosmic microwave background anisotropy, so we have our power, we have our modes, sorry, our mode C, and then we have our power spectrum. We have something that looks like that, right? Remember, the K modes represent angles. And if something is closer or larger, the angles will look of the same object, which has the same physical distance, can be larger or can be smaller, because the angle is going to change with respect to the observer. And therefore, these peaks change position. Okay, so on the CMB, you could measure or constrain the value of Q, which is degenerate with the expansion. Okay, so there are degeneracy in place. It's not an easy task. Moreover, what happens is that Q is affecting the baryonic oscillations, right? Because we have seen that the continuity equation is affected. And therefore, it's clear that the sound speed of our plasma at the time of the cosmic microwave background is going to be affected as well. That's because our coupling, now there is this fifth force that we have seen, is in place, and therefore the oscillations of our oscillator in the CMB is going to be affected. The sound speed is going to be different. And this, again, has an impact on the position of the peaks, which is given by the fact that the blobs, the typical blobs that we see, are changed by the different CS, okay, by the sound speed. And these two phenomena kind of roughly compensate one each other. Okay, one tends to push the peaks in one direction, the other one on the opposite direction, and they tend to mile down everything. So CMB observations are constraining, but not that much. Then there is, yes, there is the CMB, but there are also, since we have seen that the coupling is affecting the dynamics of matter, we could observe the effect of Q on the galaxy clustering, therefore the distribution of galaxies across the universe, and therefore the baryonic acoustic oscillations, and for example, the clustering as well of galaxy clusters, and the number of galaxy clusters. Okay, so there is an effect on cosmic structure formation. Q has an effect on cosmic structure formation that we can see here, and we are going to go in details on that. So there are going to be a series of lectures just about structure formation with modified gravity and coupling terms of this sort. Okay? Then we have local constraints, and we don't need to screw up cosmology. Okay, so these are all the constraints that we have on Q. And then there is something funny. Okay, clear? So bottom line, we introduced a coupling term here for matter and for our field, such that we have an energy momentum exchange. And we measure the Q in terms of, this energy density flux. We used this model that have been the motivation that I mentioned, which is just given by that. Okay, that's our coupling, with the minus in place here to mention the compensation of the energy momentum exchange. Then what we did was to look for the continuity equation, derive make all the study of the phase space distribution, and get our dynamics of the universe. We know what's happening out there. Okay, that's extremely cool. But now we have a problem because I didn't speak about baryons. Okay, what's the problem with baryons? I already mentioned it during the last lecture, just very briefly as a side remark. But now let's give a look into details. What is the problem with baryons, which is arising from a coupling term? Okay, so what happens? Well, we have our, what is this line? Go away. Well, doesn't go away. Okay, anyway, let's live with that. So we have our continuity equation for matter. So at least I can do it at the board. Let's do this one at the board. Yep. Baryons a problem, and that's related to the fact that once we introduce a coupling, it shows a mass evolution. So you get a particle, its mass is evolving as a function of time. Now we'll clarify what I mean by that. So let's give a look. So what we had our continuity equation. So we had rho m plus 3h rho m. There was the contribution of, there would be the contribution of pressure in general, but that's pressureless matter. So that's dust that's equal to 0. And then we have q rho m and phi dot, which is our coupling term. Now what we can do? Well, we can divide by rho m to get that. And then we can simply integrate. Okay? Therefore, we are going to an integration. We are going basically to make an integral with respect to time of all of these contribution, and we get logarithm of rho m prime between some initial point 0 and matter, and then we have q. We are integrating with respect to time, therefore this gives us a phi minus phi 0 minus 3 the logarithm of a 1 0, where a is coming from this expression h. Remember that h is a dot over a, right? Therefore we have integration by time, integration in time, integration in time. So what we just do here, we just make an integral with respect to time. Just that trivial expression. Therefore, what we have we just get the exponential of the two sides of the equation, and we get our rho m, which is rho m0, some initial condition, that is rho related to the 0 here. Then we have a to the power of minus 3, e to the q phi minus phi 0. Okay, so you see we have the e to the power of minus 3, the usual one, but now we have a coupling term which is arising from here. Okay, you say, fine, why a matter is evolving as a function of time? Well, because if we assume number conservation for our particles, so we have the same number of particles, we can relate rho to the number of particles, right? So we just get rho, and we divide it by m, by the mass of our particle, to get a number density. therefore m0 times m, number density times mass of each individual particle, so we are assuming one species of particle. So that's our assumptions. So this is this row m0 here. We have a to the power of minus 3 e q phi minus phi 0. Okay? But now what? Look, we can put this term here together. And what do we get? We get n m0 m phi e to the power of minus 3. So it's matter, its number density is going as a to the power of minus 3, so this is just a dilution due to the volume expansion, but its mass is changing, because phi is changing as a function of time. Okay? And here, m phi. Now let me be a little bit more general, is equal to the integral to some p0 and phi of q phi prime in the phi prime. Okay? That's if q is not a constant, then you have this sort of integral here, okay, instead of just the product here. So I'm here, I wrote it here in a slightly more general way. Okay? The mass is evolving as a function of time. And you say, okay, what's the problem? That's how it is. And you say, no, it's a problem. Yes?
Doesn't the fact that mass is evolving with time changes the condition of for Big Bang mobilizations?
Yes. There's an impact on that. But this wouldn't be a big problem. Then you have to check if you have observational constraints. This would enter back again on this Q. Okay? But the problem which is more relevant is actually spectroscopy. Okay? And the interpretation of all the redshifts that we are used to use. Okay? Why is that? Let's see, spectral lines. Let's go. We can take, for example, the Rydberg constant, right? If you take an hydrogen atom, the Rydberg constant that tells you what is basically the radius of your atom depends on the mass. And the position of the lines in the transitions depends on the mass of the electrons. But if the mass of the electrons are changing as a function of time, then also the position of the lines is going to change as a function of line. Therefore, it's not going to be anymore true that if we have a spectra of our galaxy with, you know, the galaxy, the continuum, and some spectral line, their location is not anymore related only to the cosmological expansion. It's not purely cosmological redshift. That's because if m is evolving as a function of time, these lines are moving in some direction. You see that? So no coupling. We have we would have like our spectrum. We would have like the spectra with the line of a galaxy. If sorry, let's take lambda. Lambda, that's the spectrum. Then if we are going a galaxy, this galaxy which is redshifted, we will get the same spectrum with the lines shifted by a certain amount, cosmological redshift. Okay? But if the meanwhile the mass is changing, then we have a contribution from the mass evolving of our electrons. and this shifts the redshift, or the line positions, which is going to create a confusion with the interpretation of this redshift as being due to the cosmological, to the cosmic expansion. Okay? Just to remind you the Rydberg constant. Rydberg, mass of the electron, e to the power of 4, 8 epsilon 0 to the power of 2 should be, yes, 2, h to the power of 3, and c. And E evolves rest frame, spectral lines evolves. They change position. Okay? That's because of this guy. That's a problem. Because you cannot anymore interpret all the cosmology that you have done. You cannot link anymore Z to A. Okay? This relationship between the expansion factor and the redshift is not anymore in place. Therefore, whenever you get your redshift measurements, you need to reinterpret completely your observations. Okay? That's a problem. How to solve it? Well, there are two ways. One is the usual one, hide the problem under the carpet. What do? You introduce a chameleon field. These are models of dark energy in which you have a coupling, but there is a screening mechanism. A screening mechanism in which you have an effective coupling term that depends on the density of matter. And the density of matter depends on position. Therefore, it's not anymore, there is perhaps a universal Q. Okay, this is fixed. But you build up your dark energy model such that what is going to create, to affect the equation of motion of your particles, the mass of the, or I mean what is going to enter in the continuity equation, because this is, you see, is a direct result of the continuity equation, is actually screened. Whenever you are next to an overdense region, say a galaxy, okay, you have your supernova which is exploding here, you get your spectral line, you measure your redshift, and you say, look, I believe that a screening mechanism exists, therefore the coupling here is 0, my mass of the electron is the one that I measure here on Earth, which is what? An overdense region. Okay? Therefore, the measurements of the electron mass that you do here is the same that you do across the universe, no matter what is the cosmic time. What the redshift you measure is the one due to cosmological expansion. Okay? So that's called chameleon mechanism. Chameleon, there is an A somewhere, I don't remember. Mechanism. Okay, screening. We are going to see that. Okay, so we are going to study screening. Now just to anticipate what is the problem here. Okay, the other one is, if you wish, theoretical, and it's a technique that we are going to study soon, basically now, after the break, which involves rephrasing the equations such that the energy momentum is respected for baryons. So we are going to modify gravity such that the coupling is not affecting the baryons, but is on something else. Okay? We are going to see the details soon. So let's say conformal transformation. Okay? Which is going to be the subject of the next lecture. Okay? Good. So we can have a break here. We can resume, let's do it in 10 minutes, so at 25 past midday.
The masses changing with time would affect also the other constants of quantum physics that would lead the spectral lines.
Well, the coupling, I mean, you see, possiamo parlare anche in italiano, l'accoppiamento praticamente avviene attraverso l'equazione di continuità, cioè il cambio di massa è legato a questo. Ok? Quindi l'unica, assumendo che non c'è creazione o distruzione di particelle dovuto a questo meccanismo di coupling, che magari c'è, però stiamo assumendo che non c'è, allora ottieni arrivi a questa espressione, che non ha niente da che però ha a che fare con G, se vuoi. Ok? Perché se guardi l'equazione del moto di una particella in newtoniano, no? Hai F per la forza, e la forza è G, due masse Gmm divided R square. Right? Let's take the absolute value. E questo va via. Per cui tu potresti avere G, che è una costante mt, o potresti dire Gt con una massa che è costante. Okay? Questo perché questi due termini sono moltiplicati in due, poi spostarlo dove vuoi. Poi devi reinterpretare tutta questa cosa qua che è un altro business.
Cambia la costante di Riccardo perché massa evolve col tempo. Se cambiasse anche la costante di Planck.
Ma perché? Qua non lo puoi, qua non ce l'hai.
Ma se la capacità è legata al masso di Ionio o a di quelle particelle, se è una costante fondamentale, le variabili si scala anche quella.
Però la costante di Planck è più legata all'energia alla quantizzazione dell'energia. Poi
Cambia la massa dell'energia di cosa.
Sì, tipicamente non viene fatta questa cosa qua. Perché per esempio in brain stick theories, per esempio, hai che G evolve in funzione del tempo. Okay? Per cui puoi shiftarla qua dentro.
Quindi questo effetto della massa avionica col tempo si vedrebbe da modificare solo la gravità e non le altre forze.
Esatto, perché qua praticamente stiamo analizzando soltanto forze gravitazionali. Perché è quello che stiamo studiando adesso, no?
Se appunto si appare il problema delle linee spettrali che si spostano non solo per l'espansione dell'universo ma anche per la variazione di massa dei barioni, se per qualche soluzione di simmetria anche altre costanti variano col tempo, saprei spiegare come, ma questi effetti non si dovrebbero compensare e lasciare soltanto lo spostamento.
Che io sappia no. Che io sappia no. Perché cioè, da qua non hai nessun legame diretto con è tutto classico qua.